So if we push on an object, um, at a single point, for example, using your finger as your single point, then you get this kind of a result. Here's my remote, and I push on a single point and I get rotation. It also might move forward if I push like right here. My foot moves forward a little bit, but it also rotates a bit. And this is true of many objects. You know, many objects have both this linear motion and rotational motion if you push on them. The only situation where that isn't really the case is if you push on the object in line with its center of mass, or it's sometimes called the center of gravity. But, you know, the center of mass of this object is somewhere probably here in the middle, and if I push towards the middle of that, I get more of a linear motion, right? So if you extend the line of the force through the object and it intersects the center of mass, then sometimes you can get a pretty good non-rotational motion like we've been expecting so far. So we have to actually take that into account. We have to take into account the fact that pushing on an object, especially when the force does not go through the center of mass of the object, can result in this rotation. And this rotation is caused by what we call a torque. What is a torque? Well, a torque is a force that causes a rotation. You know, that's pretty much what it is. That's all there is to it. There is going to be a force involved in torque. We're going to be able to calculate torque from a force and a distance. That distance is to a point that you decide on before you start the problem. Usually people will pick the point of rotation of the object, but it doesn't have to be that. It's just what usually people do pick. Why do people usually pick that? The reason that people usually pick that is because the point of rotation usually has some forces at it that may not be easy to deal with. And if you pick that point as your 0 point, then there will be no torques at that point. And so it kind of simplifies the problem. In some situations, there is no obvious rotation, so where you pick your point of origin, your 0 point, doesn't really matter. But let's take a look at a door here. You have a door, and it has a hinge, and that is the rotation point. And there are plenty of forces that happen at a hinge, and they are not all that simple to define. And so we're going to go ahead and pick the hinge as our point, our 0 point, and that is going to be the point where we're going to measure distances. And these distances are going to be from that point to where the force is acting. So in this case, we're pushing on the door here near the handle, and the distance from the hinge to where we're pushing is the r vector. Okay? It just so happens that this r vector and our force vector are 90 degrees to each other, which makes our torque calculation easier also. If you have a bigger force at this distance, you'll actually have a bigger torque as well. Smaller force at the same distance will be a smaller torque. So the force is a factor. But the distance is also a factor. You've all had the situation where you've tried to open a door not from where the doorknob is, but closer to the hinge. What happens to the amount of force that you have to apply to open the door? You need more force. It turns out that a smaller distance will also reduce the torque involved. So if you want to apply the same amount of torque at a smaller distance, you need to increase the force pretty dramatically. There's kind of an interesting door in the world out there. At the laboratory where my brother works, which is also where my father worked, they do a lot of neutron radiation experiments. They do a lot of stuff like that anyway, just because they're a lab that makes nuclear weapons parts. And they have this very famous door that was made famous by the movie Tron, the original movie Tron, and it was also in the new movie Tron, I believe. But anyway, they have this door that is a neutron shield door in one of their buildings. They actually have a few of them. And it looks like this. It's several layers thick of steel. It's like 17 feet thick or something like this of steel and actually I think it's filled with water as well, to shield from neutron bombardment. And this door from the inside, let's see if I can find a picture of it from the inside. We don't have it here. It's too bad they can't. They used to have a picture of it here on the internet somewhere. But from the inside, the door just looks like, I mean, it's weirdly shaped and everything. That's not it. But it is weirdly shaped on the inside, and it is rather wide. But it actually just has one of those little bars that you push on it to open it. Because it's so wide and it's so well balanced, you can actually push on it. And you can see that this woman here is actually just pushing the door open with her hands. But you can push it open with your hands. It has an electronic drive on it as well, just to make it easier to open. But you actually can push on it because it is so wide. You can apply enough force on it to create the torque necessary to open it. And that has to do with that distance. This distance here, I think this is, I don't know, it's like 20 feet or something like that. But, so what else matters when you're trying to open a door? Of course, the force matters. Bigger, smaller force, bigger, smaller torque. The distance matters. Bigger distance, smaller distance, bigger torque, smaller torque. But also the angle at which you push the door matters. Have you ever tried to open a door where you're trying to open it from the hinge and let somebody through without getting in the way, like maybe a wheelchair or something like this? It makes it very difficult to push on the door because you're not pushing at a 90-degree angle to the door. You're actually pushing at some strange angle to the door. It's like pushing sideways on the door. If you push directly on the edge of the door like this, the thing won't go anywhere. And that's the extreme case. And so the angle between your distance vector r, or your displacement vector r, and I guess that's actually your location vector, or whatever. But anyway, the vector r and the force vector f, the angle between those two matters. If you have a 90-degree angle, you'll have a maximum torque. If you have anything other than 90 degrees, it will be less than that. So the angle between the force and the r vector matters. And it turns out all these things turn out to bring us into a cross product. Excuse me, a cross product situation. Why is this? If you remember what we did with the cross product, it involved two vectors in a plane, and you use the right-hand rule to determine the cross product of the vector, and that cross product will be in a direction that is 90 degrees to the plane of the original two vectors. But what the cross product actually does is it multiplies two vectors together that are in a plane, and it tells you how much of one of them is pointing in the direction of the other one, and then gives you a vector in the other direction. And that is that length. So the length of this torque vector, in other words, tells you how much of this force vector is pointing in the direction of the r vector, is actually pointing 90 degrees to the r vector. I guess should be a better way to say that. So it tells you how much of the force vector f is pointing in the direction of the r vector, and then it multiplies the two together and gives you the torque vector, which is 90 degrees to it. And the magnitude of the torque of the cross product looks like this. Let's see, where is it? We don't have the formulaic version of it. Here it is. So the magnitude of the cross product of the two vectors ends up being the r vector magnitude times the force vector magnitude times the sine of the angle between them. So that tells you actually the length of this torque vector, or the length of the cross product. The direction of the cross product is determined by your right hand rule, where you put your right hand, point your right hand out in the direction of R vector, and then you turn your fingers in the direction of the force vector, and then your thumb will point in the direction of your torque vector. So if this force, instead of pointing off in this direction, was pointing in the opposite direction this way, then we'd have an R, we'd have to flip our hand over to turn our hand in the direction, our fingers in the direction of the force vector, and the torque would be down in that case, in this particular situation. So we have a right-hand rule, we have a cross product. How do we deal with the cross product in reality? There are a couple different ways to think about this. One of the ways to think about this is to say, what component of this force vector is perpendicular to R? So if I draw two components and one of them is perpendicular to the R vector, so one of them is like this and the other one is like this, then this part of that R vector, or this part of that force vector, is the part that you multiply with the R vector. And then you use your right-hand rule to get it in this direction. That's one way to think of it. Another way to think of it is, of course, to think of just multiplying their magnitudes and taking the sine of the angle between them, which is very simple to do. But in some cases, they don't actually give us the information to do that very easily. An example of that might be, where they give us the R vector in its component form. So they tell us that R vector is 6i hat plus 3j hat or something like this. And then the force vector is 5k hat minus 8 I said k hat, so minus 8j hat or something. I did that in the wrong order. But minus 8j hat plus 5k hat or something. And then we'd actually have to do the cross product using the component form of the vectors, which you can convert those into angles and magnitudes, but it's not necessarily the easiest thing in the world. There are easier things to do with that information. So a few different ways to think about this torque. Most of the time when you're dealing with torque, you're going to deal with vectors that have magnitudes and directions as far as angles go. That's the most common way to deal with vectors. It's not the only way, but it is the most common way. And so that's what we're going to do here for the rest of this section, is just look at those examples of that. So here we have four forces that have different directions, different magnitudes with respect to this coordinate system. And we want to know the torque that each of these forces would exert about the origin. So this is our 0 point we're measuring from. So each one of them has a different distance and a different angle. Fortunately, all these forces are acting on the axes, so we just have to look on the axis to measure the distance. We don't actually have to do any calculations to measure the distance. But if, say, for example, let's say that this force right here, this 30 Newton force, was acting at the point -5, -3 down here. Then we'd have to figure out the distance between 0 and that point for our R vector. And then the angle would be different as well, because we'd have an angle for this one and an angle for this one. We'd have to figure out the angle between them. So that would make it definitely a little more difficult. These ones are easy though. So how do we do this? Well, we use the formula that the torque is equal to R times F times the sine of the angle between them, which is the cross product. And we figure out all the R's. So for this one over here, the R is a 5. It's a 5 in length, and it has an angle that is, it's just an angle that's going off in the negative x direction. So the angle between this one and this one is the angle here. Now it doesn't really matter if you choose the 53 or the angle that's over here, which is 180 minus 53. It doesn't matter which one you choose, as long as you use the right-hand rule correctly to figure out which direction your torque is pointing. So for this one, the R vector goes from 0 out to here. So your hand would point in the negative x direction for the right-hand rule. And then the 30 newtons is down, so you turn your fingers down, and your thumb would be pointing out of the page. So your torque is coming out of the page for this force here. They actually do this one first, the 4 times 40. So for this one, we have our R vector going from 0 out to the force. That's a 4-unit long R vector. And then that's 4 times 40, 160. And then the angle between them is 90. What's the sine of 90? 1. And so it doesn't change anything, right? The sine of 90 is 1. And then the direction for that one would be the right-hand rule. You point it out towards the positive x direction. You curl your fingers up in the positive y direction, because that's the direction of the force, and it's coming out of the page. Right? Turns out that this other one is coming out of the page as well. Your R vector is 1 up this way. There's a 60-degree angle between it and the, well, there's actually a 60-degree plus 90, so it's 150 degrees between the R vector and the force vector. So be very careful with that. They've given you an angle here from the x-axis, but the angle that you want is between the R vector and your force vector. So this angle, your R vector is here, your force vector is here. You want this entire angle, 90 plus 60, 150. Then you take the sine of 150 times the 1 times 20, and that will give you the magnitude of that vector. And of course, that vector is also pointing out of the page. The only one that's not pointing out of the page is this one down here. You have a R vector that's 3 units long, going straight down. So if you point your hand in the direction of that, and then turn your hand so that you can turn your fingers off in the negative x direction, then your thumb will point into the page for this one, and you have a torque that is pointing into the page for that final one there. But all of them, you just take the magnitude of the distance from 0 out to the vector, then the length of the force vector, you multiply those two things together, the R times the F, and then the sine of the angle between them. In the case of this one, it's 90. In this case, it's 90. In this case, it's 180 minus 53. And in this case, it's the 60 plus 90. Right? And they do all those calculations down here, and also they do the right-hand rule thing. So the total torque of all of these, the total torque, since all of them are pointing out of the page except for one. So what you have to do to add torques together like that is you have to decide which way is positive. Now we use the right-hand rule to determine which way is the positive z direction as well. You put your right hand in the direction of the x, you turn your fingers in the direction of y, and your thumb points in the direction of positive z. So positive z is out of the page in this case. So all the torques that have their right-hand rule pointing them out of the page are all positive torques in the z direction. And then this last one is a negative torque in the z direction. So to get the total, you take these three as positives and subtract this one off. And that will give you your net torque. And that's what they do here at the end. They have the three that are positives, the 160, the 120, and the 10. They subtract off the 60, and then they have the net torque. Now what is torque measured in? Well, torque is force times distance. So it's measured in Newton meters, and there is no unit no name for that unit. It's just Newton meters. You may have heard of it in the United States as foot-pounds sometimes, or pound-inches sometimes. Those two are used for torque quite a bit. Excuse me. But in the rest of the world, it's Newton meters for the most part. So here is an actual object. It might be a disc or a ball or something like this. In this case, I guess it's a flywheel, so it's probably a disc. And we have three forces acting on it. One of these forces is not exerting a torque relative to the center of the ball. Which one? When I say relative to the center of the ball, I say that means that the R vector will be measured from the center of the ball to where the force is acting. Right? So if you have an R vector going to each of these forces from the center of the ball, one of these forces is going to have a torque equal to 0. Which one will it be? Why?
If the radius we're going to connect
What would it would be anti-parallel. That's exactly right. Anti-collinear is the proper word, but it is collinear with that line, right? That means the distance between those two lines is actually 0, which really what we're talking about is the angle between those lines is 180 degrees. What is the sine of 180 degrees? 0. So the torque will be the length of the radius, with the r, the distance from the middle to the force, times the force, but it doesn't really matter because it's also times the sine of the angle between them, which is 0 in this case. Sine of 180, so it'll be the sine of 180, which is 0. All the rest of these forces have an actual distance between the line of force and the center, right? So this one right here has the distance radius this way, but it's closer to 90 degrees. It may not be exactly 90 degrees, but it's pretty close to it, as you can see. This one here, the radius out here is obvious. They've told you what the angle is. It's 30 degrees. Sine of 30 degrees is like 1/2 or something like that, right? So that one's definitely not going to leave you with a 0. This one's going to be the sine of about 90, which is like 1. It's not going to leave you with a 0. This one, the sine of 180, is going to definitely leave you with a 0. So any force that encounters an object, and then if you extend the line of that force in both directions, and if that line of that force, and we actually call it that line of action, if the line of action passes through the point that you're calling your 0 point, where you're measuring all your distances from, it will end up having a 0 torque effect on the object. It doesn't mean that it won't spin the object. That's not necessarily true, because remember, you don't always pick your point of origin at the point where the object is spinning around. So that depends on where you're picking your point of origin. In this case, we're picking our point of origin at the center of the disk. So we have a force pushing on the edge of the disk this way. We have another force pushing kind of on the edge of the disk at an angle this way. And then we have another one pushing on the edge of the disk right through the center of the ball. And they want to know, what is the net torque? Well, the net torque is going to be the sum of these 3 torques. And remember, the direction does matter. And so we've got the values of the forces, and we've got the angles, and we've got everything else. So we just RF sine theta for each one of those, right? For the one that's a 30-degree angle right here, they are actually wanting the angle between the R and the F. And technically, what you should do is you should move this force up to here so that this one and this one are kind of head to tail. And then it's a 30-degree angle right here. But they just decide to use a 50-degree angle here, and that 150 rather degree angle here. That also works because it's still an angle between the two, technically. Technically, you can also use the angle 180 plus 30 degrees over here. That will also, I think, give you the correct answer. But you have to realize that calculation is just going to give you the magnitude of the vector. It's not going to tell you direction. You still have to use the right-hand rule to get the direction. If you choose your angles correctly, using the geometry correctly, then it will actually tell you the magnitude as well. I mean, it'll tell you the direction as well, but that usually confuses people, so we don't really teach it that way. So for this one, they're using the sine of 150, and that's the first calculation they do. R1, F1, sine 150. All of these R's are the same R's because they're just the radius of the disk. It gives you the 5 Newton meters, and the direction, of course, you put your hand in the direction of the R, turn your fingers in the direction of the F. The F is pointing upward to the left, so that's that way. This one's coming out of the page. For this one down here, of course, you have an angle of 180, so that one ends up being 0, which they talk about, but they don't write it down anywhere. And then the last one, they say has a 90-degree angle. So the R times F, you have an R this way, and an F up this way again. Sorry, you have an R this way and an F up this way, right? So the R is going out to the left, the F is going up, so that one's into the page. And this starts to make sense with this problem. This torque, this force over here creates a torque that's going to try to turn this ball counterclockwise. This one has a torque that's going to try to turn the ball clockwise. And this one has a positive torque. This one has a negative torque. So opposing torques try to do opposite things to an object. Okay? And that's especially obvious when you put your center of your origin, your point of origin at the center of rotation. Makes it quite obvious. All right, so here's another one. A large ocean-going ship runs aground near the coastline. Lies at an angle. Salvage crews must apply a torque to the right to right the ship in order to float the vessel for transport. Force of 5 times 10 to the 5 newtons acting at point A must be applied to the ship. What's the torque? About the point of contact of the ship with the ground. So we have this 100-meter distance that they've measured for us, and this force of 5 times 10 to the 5, and they tell us the angle is 10 degrees with the vertical here. So you have to remember some geometry when you're dealing with torques for sure. You have a 10-degree angle here, which means if we slide this parallel line over to here, that puts a 10-degree angle here plus a 90-degree angle here. So a total of 100 degrees between A and the R vector, right? You have a total of 100 degrees there, and you take the 5 times 10 to the 5th, multiply it by 100 meters, and then the sine of 100 degrees, and that will give you the amount of torque that you're applying. So once we figured out torque, how to calculate torque, well, actually, we should do one more thing actually before we. So one more thing that we should do is we should calculate, because I think in your homework you have a problem where you have to calculate torque from the, what chapter are we in? 10? I think that there's one where you have to calculate torque from the component form of the vector. Let me see if that's true here. Maybe not. Oh yeah, here we go. So here we give you one problem where you actually have to calculate the torque from the vector forms here. So we have R is 3 I hat, 2j hat, 4k hat, minus 4k hat. And then the force is negative 12.5 I hat. And they want you to calculate the torque. Well, you go back to do this, you go back to the very beginning chapter. If we go back to chapter 1, chapter 2 rather, go to vectors and go down here to the product of vectors. Products of vectors. In the products of vectors, they actually give you the formula for calculating the cross product of two vectors. And then it's R cross F. You can't do F cross R. That gives you a different answer. It gives you the wrong answer. You have to do R cross F. So here's the vector product or the cross product. And that's the angular version that we just, that's the RF sine theta, just like we saw. So that's very similar to what we've done. But down here we have the actual right here. Down here we have the formula for the cross product of two vectors in three-dimensional space. you take the y component of A, the y component of the first vector. So in our case, it would be r cross f. So we would take the y component of r and the z component of f, and multiply them together. Just the magnitudes of those components. And then we subtract off the magnitude of the z component of r and the y component of f. Once we get a number out of that, then we slap on the vector, the unit vector I hat to that. And then we do rz fx minus rx fz j hat plus rz fy minus ry fx k hat. So that will give you the answer. Now some of these will end up being 0 in your particular version, because the force vector only has, in our problem here, the force vector only has a I think it only has a k hat component. So if our force vector only has a k hat component, that means our force vector for y is 0. So this term will be 0, and this term will be 0, and these two terms will be 0. So you only have two terms, an I and a j hat, for example. And then our other one only has an I hat j hat component, our r vector. Oh no, it had all three components anyway. But anyway, you'll have some things that'll drop out. So some things you won't even have to calculate. It'll make it easy. And here's another version of that where they separate out each component of the cross product. So, with that problem, which I believe was problem 2 or 3, we'll only have to do part of it. All right. Let's go back to chapter 10. All right, so anyway, now that we've learned about what torque is, what else can we do with it? Well, it turns out that since torque is something that is caused by force, and the torque is kind of like the rotational version of force, you could kind of think of it like that, then we can actually move on and make an analog for Newton's second law in rotational form. So force equals m times a for just, normal Newton's second law. But acceleration, linear acceleration along the edge of a circle, is equal to r times the angular acceleration. So we just make that little change there. And if we do this, if we multiply on each side by r, rf mr squared alpha, now we've got a new equation. Why would you do that? Well, we do that because we know that r times f is equal to torque. And so we get torque on the left-hand side, and we get something times alpha on the right-hand side, and this something is going to be what we call our moment of inertia. So we've been to this moment of inertia place before. This is the moment of inertia of a point particle that has a force acting on it. Right? M times r squared. So Newton's second law in rotational form is the sum of all the torques, or the net torque, equals the moment of inertia, total moment of inertia of the system, times the angular acceleration of the system. Okay, and here they actually derive it from the vector side now. You have tangential acceleration is actually equal to angular acceleration crossed with the r vector. So this can be shown or proven by geometry, the geometric things, but it also can be proved mathematically. But if we go ahead and use the cross product, well, this is a cross product identity that you don't know, but it is mathematically true right here. If you have a triple cross product, R cross alpha cross R, then you can turn it into two dot products multiplied by alpha and R. So they do that. Once they've done that, they have alpha R squared, and then they multiply by the mass to get mR squared times alpha, and that actually is then equal to R cross M times A in the end. So they've just proven that it's true. Okay, we'll believe them. Proofs get physicists really excited, as you can tell. Anyway, so how do you solve problems like this? Solve them the same way you do with linear dynamics. In linear dynamics, what we did is we drew a picture and we labeled all the forces. Right? We labeled where they were, how much they were, which direction they were, and all that stuff. And then in linear mechanics, linear dynamics, we often split the forces into components. With rotational dynamics, we can do that also if necessary, but it's not always necessary. If we're just worried about the rotation of the object and not the linear motion of the object, then we don't have to worry about that. We can just move on. But we should draw a picture and include all of the forces. But we need to remember to now we're dealing with pictures of objects, not just a point. So if you're applying a force to a car, you're not going to have a free body diagram that's a point. It's going to be a car or something similar to a car. Remember when we had a force acting on a wagon or something like this. Here's our wagon, here's our picture. We have a force. Our free body diagram became a point, right? Well, in this case, in our case, it's not going to be that. We're going to keep the wagon or something similar to a wagon. So you might turn it into just a rectangle without wheels, and then you have a force. But now we have to say, where's our 0 point going to be? Maybe it'll be here. What's our distance to that force going to be? Because now we're going to have to label forces and R vectors for every force. And there should be an R vector for each force. That R vector should go from your 0 point out to each force. Then, instead of saying force equals mass times acceleration, and if the acceleration is 0, then force just equals 0, right? Then instead of saying that, we say the sum of the torques equals I times angular acceleration. That's the equation we're going to work with now. Or the sum of the torques equals 0 if there is no angular acceleration. Either way. Either way, it gives us an equation to work with where we plug in the numbers from the problem into the equation and create an equation to solve for the unknowns. So here is a merry-go-round, and we have a person pushing on the merry-go-round with the force F at a distance R from the center of the merry-go-round. The force is 250 newtons. We've drawn it in. And the distance is the radius of 1.5 meters coming out from the center. So that's our R vector. R is 1.5 meters. We want to calculate the angular acceleration produced when no one is on the merry-go-round. Why do we need to know who's on the merry-go-round? Because we need to figure out the actual moment of inertia of the merry-go-round, because the equation is the sum of the torques equals I, which is the moment of inertia, times the angular acceleration. We don't know I, and we can figure out the torques, so we got to figure out I. Turns out that the moment of inertia for a solid disk rotating about its center axis, which is kind of what a merry-go-round is 1/2 mR squared. So that's a good approximation. Mass of 50 grams, radius 1.5, so we calculate the I, mR squared. Or 1/2 mR squared, so we calculate that. 1/2 mR squared. And then to find the net torque, we plug it into our equation. The sum of the torques, now there's only one torque. It's just the one force, 1.5 meters away, 250 newtons, and the angle between the force and the radius is 90 degrees. So the sine of 90 degrees is 1. We calculate our torque to be 375 newton meters. Then we plug everything into our equation. 375 newton meters is the torque we solve for alpha. Divide by I, and we get 6.67 radians per second squared of acceleration for this measurement. What if we put a child on it? If we put a child, an 18 kilogram child, 1.25 meters away from the center, now we're going to consider the child on this thing to be kind of a point mass circling the same point. So the moment of inertia for the child, because they're going to be kind of like a point mass, is going to be mr squared, the mass of the child times the distance from their distance from the center. That distance is 1.25. So we calculate the moment of inertia of the child, mr squared, 28.13 kilogram meters squared. Then the total moment of inertia for child plus merry-go-round is the moment of inertia of the child plus the moment of inertia of the merry-go-round, total for 84.38. We know the total moment of inertia, and we know the torque from here. No, that's not correct. That's not the torque, but we do know the force. The force is still the same. Where's the force? Right here. The force is still the same at 250 newtons. So the same force, but a different moment of inertia. Actually, they're saying they're going to apply the same torque. Oh, yeah, it is the same torque because he's still pushing at the 200. He's still pushing at the same distance, so it's the same torque. So same torque, different moment of inertia, different angular acceleration. This angular acceleration is 4.44 instead of 6.67. It is less. Does that make sense? Of course it does, because there's a child on there, so it's got more mass, and it's going to take more to accelerate. So that takes care of torque now, and next week we'll work on work and power for rotational motion, and we'll be done with chapter 8. You too.